Clearly the most obvious of those is the clean room on the first floor of the LCN, but we have many other facilities that people will talk about today. I guess the main purpose of today's activity is just to make you aware of what we've got, give you some idea of the facilities we've had, so you can start thinking about whether they'll be of use to you in your research projects, whether you're a PI, postdoc, or a PhD student. And secondly, to give you some idea of the mechanics for how to access those facilities if you haven't done so already. Of course, everything is convoluted by the pandemic situation, but I mean, thanks to fantastic effort by the technical staff at the LCN, we've essentially managed to keep everything running to a greater or lesser extent since we came out of the first lockdown back in July, I guess. So although there are restrictions on total numbers we can have in the building, and there are restrictions on the extent to which we can deliver training, which is essentially set by the 2-meter minimum working distance regulations, essentially we're open for business. And so if we can have as many users coming into the building as possible to take advantage of the fantastic facilities we've got, then our job is to try and make that happen. So I guess the ground rules for the presentations are I'll hand over in turn to each of the speakers. We'll try and keep to time because of the 2 o'clock meeting that follows this for LCN and UCL people. If we have questions, I suggest we'll deal with them at the end for any of the speakers. So after we've finished all the presentations, we'll have some time, I hope, for questions. Either put them in the chat or raise your hand, and then we'll go through the questions at the end for all the speakers. So I'll now invite the first of our technical staff to present, which is Richard Thorogate. Are you there, Richard? Do you want to share your screen?
Yes, I'm just going to share my screen.
About AFM, Confocals, MPMS, and PPMS.
Okay. Can you see my screen?
Yes, we can.
Excellent. Okay, so I run 2 facilities at the LCN currently. So I've been running the AFM and confocal facility since 2008 and PPMS, MPMS facility since 2011. So start with the AFM facility. So this just started out with 4 instruments back in 2008, and now it incorporates 11 AFMs, which cover all range of materials from hard matter to biosamples. And it's possibly the biggest AFM facility in the country now. So just quickly flicking through the list of what we've got, I'll expand on these in a minute, but with the Brooker instruments, we have Dimension Icon, Dimension VARScan, 3 multimode 8s, and Resolve, which is a BioFM. And we also have Brooker JPK BioFMs, so NanoWizard 4, NanoWizard 1, NanoWizard Ultra Speed, and 2 Cellhesions. So this is our typical user groups here. So academia over this side. So about 90% of our users come from UCL, King's, Francis Crick, Imperial, Birkbeck. And over here, we have a small commercial base of users. So these are some of our past and present users. So just cherry picking some of these. So Syngenta worked with us a few years back now. So they were looking at seed coatings and powder formulations. Wave Optics are one of our current users, so they're developing AR glasses, characterizing waveguides. And Fabric Nano, they work in the field of DNA nanotechnology. So this is our Dimension series of instruments. So this is a Dimension Icon over here. So there's a tip scanning AFM, a max scan size of 93 microns X and Y and 13.5 in Z. So we can do standard contact mode and tapping mode. You can do this on all our instruments. This one also has peak force tapping, which is a newish AC mode imaging technique. So it uses lower frequencies in tapping mode, so typically 1 to 4 kilohertz. And here the tip sample distance is modulated as a sine wave, which allows piconewton force sensitivity. So it also has scan assist image optimization, which will control gain, set point, Z limit, and scan rates. It's kind of designed to make imaging a lot easier. So as extension of peak force tapping, we also have QNM. So as we're generating force curves in peak force tapping, we can characterize the mechanical properties of the surface. And we also have standard force spectroscopy and mapping, which are contact mode-based techniques for mechanical mapping. Other techniques, so we've got electrical force microscopy, magnetic force microscopy. So these are two-pass techniques. So you map the heights first, and tip lifts to a set height to measure magnetic or electrical force. We can also do Kelvin probe to measure the surface potential of the material. So again, this is a peak force tapping technique. So in theory, you can measure the height, surface potential, mechanics all at the same time. Peak force tuner. So measure the conductivity of the surface. So it's also a peak force tapping technique. So this is useful for carbon nanotubes and nanoparticles. Conductive AFM, that's the old contact mode based techniques. It's not great for loosely bound materials. And we also do scanning spreading resistance microscopy, scanning capacitance, piezo response, and nano manipulations. So we've got a lot of options on this instrument. So this is the dimension icon over here. So again, this is tip scanning AFM. So you can achieve frames per second scan rates on this instrument. So, and this is also an area fluid, so it's useful for dynamic processes. So it uses a separate Z scanner for increased resonance, high-speed electronics, and short high resonant frequency cantilevers. So again, here's our standard modes here. So again, contact tapping, peak force tapping, we do mechanics, various electrical modes as well. So just extending on the Q&M to show you kind of things it can do. So this is our vertical force versus time. This is our probe motion going down towards the surface, and this is our force response here. So this is the maximum force we've set, and this is the adhesive force here. So look at these force curves. So this is vertical force versus Z. We can and fit deformation, DMT, modulus, adhesion, dissipation data to these curves here. So we can achieve these maps. So this is just the height map. Then we have adhesion. So this is a polystyrene LDPE sample. So you expect LDPE to be more sticky, which it shows that. And this is the modulus here. You expect LDPE to be a lot softer than polystyrene, which is there. And then we've got dissipation and deformation. Obviously, LDPE would deform more than the polystyrene. Okay, so we have 3 Brooker multimode 8s. So we have 3 different scanners for this. So we have a J scanner with a heater, an E scanner, and an A scanner options. So this is because it's a sample scanner, it accepts much smaller samples, so about 1 centimeter in diameter. So again, here's the various options we have for this. And just an example, so this is work done by Alice Pine some years ago. This is done on DNA, where she managed to resolve the double helix. So this is just DNA on mica in a nickel chloride buffer. And you can clearly see the corrugation on the DNA helix here. And you can also see the major minor grooves of the DNA. And also, it's quite important to get the force right. So here you see we're applying 39 piconewtons of force. So DNA should sit 2 nanometers from the surface, which it clearly does there. But if you start applying too much force, you start to see squash the DNA. So it's very important to get the force correct. So this is our newest edition, which arrived last summer. So this is the Resolve BioFM. So there's the scanner and motorized stage here. So it's got an 18 micron Z length, so it's suitable for cell topography and mechanics. So it sits on top of a Olympus FP1000 fluorescent microscope, and it has a couple of cameras. We've got high resolution water-cooled and/or Xyla there, and an IDS camera there for general purpose usage. So you can overlay the optics or the fluorescence with the AFM images using something called mirror view. And filter sets we have for fluorescence, DAPI, GFP, rhodamine, and Sci5. So there's just a couple of examples here. So this is done in peak force tapping. So it's just a couple of MDCK cells here, and we can clearly see microvilli on the surface of these cells, these like finger-like protrusions. This is done by Christian Bortolini, and this is just an E. coli. So we've done peak force tapping on this as well. So this is height and QNM. So you can see sled and modulus, deformation, and adhesion. So again, here's the various modes we can do on this instrument here. So moving on to the Brooker JPK NanoWizard series. So we have a NanoWizard 4 and an Ultra Speed. This one's the Ultra Speed, although NanoWizard 4 looks very similar. So again, this is on a motorized stage here and on a inverted microscope, another RX73. So we can in theory overlay optics and fluorescence again. So the Ultra Speed itself is a fast scanning AFM for investigating dynamic processes. You can achieve line speeds of up to 100 Hertz. And then NanoWizard 4 is more sort of for general BioFM work, so imaging cells, cell mechanics. Again, imaging modes here. This one has something called QI mode, which allows precise control over tip sample force at every pixel of the image. So just an example here, this is a HeLa cell image on a NanoWizard 4. So you can see the edge of the cell here. If you zoom in a bit, you can see the cytoskeletal structures here. And this one was imaged by Georgina Ben. So this is an E. coli image in AC mode on the ultra speed. So this has been exposed to the membrane attack complex, which forms pores on the target cell membrane to induce cell lysis. So you can clearly see some pore structures there. So last AFM we have, so we've got two of these Bruker cell adhesions. So this one has a long Z piezo, so 100 microns, but no XY piezo, so it can't be used as cell imaging. So it's useful for cell-to-cell, cell-to-substrate interactions, investigating cellular mechanics. So this is actually on the confocal microscope at the moment, but this stage in theory can be put on any standard inverted microscope or upright optics. So just an example of some work being done with Guy St. Thomas's here. So they're looking at mechanics of bisected ovaries. So what we've done here, we've actually glued a bead to one of the ends of the cantilevers, and we measured the modulus at 74 points in the outer portion of the ovary. And we can see quite reasonably tight data of the modulus here. However, I've looked at different areas across the ovary. So here we've done a force map to produce a heat map, if you like, of the modulus. And you see there's a bit of higher variability in some areas. So that might be an area containing follicles. So we're going to do some further work on this to overlay optical images with force maps. So as time is short, I'll just quickly scoot through the confocals we have. So we've got 2 times Olympus FP1000s. So as I said, you can put the NanoWizard or cell adhesion AFM head on top of here. Or you can just use it as standalone confocal. So it's got standard laser lines, covered DAPI, FITC, rhodamine site 5. You can have environmental control over this if you wish. So this one in the picture is equipped with a motorized stage, and it also has a sim scanner, so simultaneous excitation, so you can do flip-frap photoactivation and photoconversion. And this is just the updated version, so this is Olympus FP1000, again for laser lines, environmental control, sim scanner, motorized stage. This one has ultra-high sensitivity gas detectors as well. Oops. We also have a Andor spinning disc system. So this is a high-speed confocal, so it has low bleach rates and low phototoxicity. Again, for laser lines, environmental control. This has a photometrics prime camera, CMOS camera on it, which replaces our old ECD camera, which shows 95% quantum efficiency. Okay, so the last facility I want to talk about is the MPMS facility, so it's magnetic.
We're trying to round up in the next minute or so, Richard. That'd be great, so we can move on. Thanks.
Yeah, sure. Yeah, that's okay. So this is a magnetic property measurement system. So it has a 7 Tesla magnet. It's actually over 25 years old now, but it still runs fine. So it's a high sensitivity squid magnetometer, temperature range 1.8 to 400 Kelvin. So it has an RSO transport. So frequency is 0.5 to 4 hertz. We can do a step DC scan, so we can set powders, single crystals, pellets. Unfortunately, this one doesn't have a helium reliquefier, so it's extremely expensive to run. So we only cool it down as a large batch of samples to run on it. And the last instrument is the PPMS, so physical property measurement system. So again, the standard temperature range 1.8 to 400 Kelvin. This has a helium reliquefier, so cheaper to run than the MPMS. 14 Tesla magnets, and we can do many options on here. So we have a VSM, so it's lower sensitivity in the squid, but the measurement's a lot faster, so you're doing it at 40 hertz. We have AC susceptibility, sensitivity fields and frequencies you can do. Electrical properties, we can measure DC resistivity, AC transport, so resistivity, Hall effect, IV curves, differential resistance. Thermal property, heat capacity, and TTO option. And then there's various other options. So helium-3 will extend the temperature range down to 0.35 Kelvin. You can use that with heat capacity, ACT, and resistivity. Have a horizontal rotator, razor bill strain gauge, and you can also equip it with a home-built breakout box so you can interface with the key for the instrument. And final slide. So obviously you have to mention COVID at some point. So with PPMS and MPMS, I'm not currently training any new users for experienced users only at the moment, but I do offer a measurement service on certain options. It's also on TeamViewer, so in theory people can go in, load up their samples and run it from home. With the AFM and Confocal, training still taking place at 2 meters, so we can screen share, do SAPs, videos for training. That usually takes 2 days for just training in topography imaging, and half a day for further options, and a bit more shadowing after that. I offer on-site assistance, remote assistance, and a measurement service. So any more questions, then contact me on this email. Okay, thank you.
Yes, thank you very much, Richard. A wide range of interesting things there. I guess if people on the call have questions for Richard, note the email address as he's got there, but also you can post some questions in the chat. Maybe we'll come back to them at the end of the presentations. So we're a bit pushed for time, so we'll move on to Steve Etienne now, who's going to talk about the Cleanroom fabrication suite.
Hello. Can you hear me and see my screen?
I can hear you. I just see
Screen share.
Great.
Oh, we could see it, Steve, and now it stopped sharing.
Can you see it now?
Yes.
Yes.
Okay. So I'm going to talk about the cleanroom facility. First of all, when we're talking about facilities in the LCN building in Bloomsbury, and it actually consists of 3 different spaces. On the top level, we have what we call level 1. It's a clean room of 250 square meters with good quality cleanliness, class 6 and class 5. And that's where we do the bulk of our fabrication work. There's a separate focused iron beam lab in the basement, and also what we call a back-end lab where we do the more dirty processes that are commonly associated after wafer fabrication. So we've had pretty good operations. Before COVID ruined everything, we could expect in a given year to have about 200 different active users, and each user would spend on average 65 hours per year in the lab. So it's a relatively high level of commitment to be a user. Obviously, each individual users vary. Some users are in there almost every day and some are not quite so active. But we've had 42, these users are associated with 42 different PIs across 20 departments. And these came from 11 different institutions, 8 of which are academic and 3 of which are commercial. So there's a large number of equipment available to book up. Last count, 58 individual bookable items of equipment. So a bit of history. It was opened in the new LCN building in 2005, and about 75% of our current equipment was installed at that time. So it's regarded as essential research available for everyone. And one of the major factors is it's got a dedicated support team of currently 4 technical staff to make sure it's operational. Since 2005, we've had intermittent upgrades in equipment, usually funded from individual PI grants. And the last one was in 2018 when we had a new electron beam lithography tool put in, a new furnace system and rapid thermal process equipment, and also a direct light laser equipment for optical lithography. So just briefly cover the organization of the lab. There's too much to go through in absolute detail, but that can be provided offline if you need it. Level 1 occupies the whole of the level 1 floor plate in the LCN building. So the red areas are service areas where the support the activities inside, and we internally talk about tunnels. So in tunnel 1, this top blue area, we house all our plasma tools. We have a variety of etchers and deposition equipment in there, and also plasma cleaning equipment. In tunnel 2, this is our yellow area, and we have a whole bank of wet benches along one side where we support all sorts of chemical etching procedures, as well as photolithography, spin coaters and ovens for baking. And on the other side of the corridor, we have our exposure equipment, which currently consists of 2 mask aligners, suitable for samples from very, very small, several millimeters in extent, up to 150 millimeter diameter wafers. And that's where our new direct light laser lithography tool is located as well. There's a dedicated room for EBL, or electron beam lithography. That's where our new 100 kilovolt Elionics tool is located. And finally, in tunnel 3, we house all the thermal processing equipment, some characterization equipment suitable for measuring thicknesses of layers, resistivity, etc., and all of our metal deposition equipment. So we have thermal evaporation and sputter coating and electron beam deposition equipment for metallization purposes. Also tucked in the corner is our older electron beam lithography tool, which is a 30 kilovolt Wraith, and that's also still in operation. So one of the other spaces we've got is our back-end lab. It's just a lab. There's no special user dressing up required for that, but we have in there electrical probe station, a dicing saw, and 2 wire bonders and 2 scribers, and quite a lot of other stuff associated with the maintenance of our clean room. Finally, in the basement, we have a focus ion beam lab, and that houses 3 tools, 2 of which are available to everyone and 1 of which is public, privately owned, offering high resolution scanning electron microscope, ion beam microscopy, which is even higher resolution than SEM, and focused ion beam capabilities. So during COVID, we've managed to keep all the equipment open and running, but we have a lot of controls in place to make it safe for everyone. And these controls do vary according to the current status. So at the moment, we're probably in the most restrictive status of all. And we are guided and keep very much up to date with changes in policy and university requirements. So principally, the precautions are to limit the number of people in the labs. Our labs inherently have a high air change rate, so that's also beneficial for reducing infection. And we've introduced enhanced PPE with gloves, face masks, and individual gowns required for all users. We adhere to 2 meters distancing at all times, and we also record everyone's presence during the lab for later reference if necessary. So during the current extreme lockdown, we can only allow experienced users, and we have limited staff availability, and we've had to temporarily suspend face-to-face training because it's been determined that all equipment training in the clean room really needs 1 meter face-to-face, but we hope we can reintroduce that once the lockdown eases, and then allow less experienced people to come in as well. So I mentioned earlier that we charge for it. This is an overview of the costs, and we treat all people from UCL, Imperial College and King's College the same, so they all pay the same rates, whereas external academics and commercial users will pay more. So how do you access? The first step is you have to become a visitor to the LCN department, and all our websites point to routes to show you how to do that, and you have to attend the LCN building health and safety induction. And everyone will be issued UCL computing credentials, and these are used to access our online tools, such as PPMS, not Richard's. This is it's a booking system. And in there you can apply for user accounts, and that will open up your access to request and book cleanroom training and equipment training. and also to manage your financial history. We do operate on a prepaid basis where we ask money in advance for users, and we will track your payments as and when you use it. Remember that a typical user spends 65 hours a year in there, so it's an investment of certainly several thousands of pounds for a typical user to use a clean room. And I'm going to finish here with some contacts. We have websites showing our equipment and current COVID restrictions, and my contact details are there, and also a link to the current booking system. And that's it.
Good, thank you very much, Steve. Again, huge amounts of facilities in the clean room that Steve's only really been able to touch upon. So if you want to follow those links or email Steve, or again, if you want to post a quick question in the chat for Steve, we'll come back to those at the end of the presentations. Okay, so the next presentation is by John Morton on the Quest cryo measurement facilities. Over to you, John. If you are there. Excellent. I can't hear you, John, if you're talking.
Can you hear me now?
Yes, we can.
Brilliant. So I'm going to be giving an introduction to the Quest low temperature facilities at the LCN, and happy to answer any questions you have. It's just a quick overview. So what is Quest? Quest was came from a significant £8.5 million investment from EPSRC, combined with a larger estates project from UCL. And as a whole, the grant provided equipment for micro nanofabrication, thin film growth, that is located primarily within the LCN cleanroom, and also the low temperature measurement test beds that have gone on to become the Quest facility that I'll be talking about. And initially on this grant, there were the following partners, and the focus was on quantum technologies. So as I mentioned, part of this project went into upgrading tools in the LCN cleanroom that you've already heard about. So I won't dwell too much on those, but they can be accessed via the LCN cleanroom system that Steve has introduced. And so what we call now the Quest facility is composed of these low temperature test beds, and in particular 4 closed cycle dilution refrigerators. So these have a base temperature of less than 10 millikelvin. They all come from Blue Force Cryogenics, and the facility was officially opened in November 2018 by Jeremy Wright, who was then the cabinet minister for digital culture, media and sport. I'm not sure exactly which of those he was representing when opening facility, probably digital. So there he is shaking my hand as we unveiled the plaque at the entrance to the F10 lab in physics, which is where most but not all of these refrigerators are located. These are more photos from the opening. He's talking to one of the postdocs, Katie, in Paul's lab. But really, the aim is to show you one of the systems there that's highlighted in red in the background. This is one of the larger dilution refrigerators, and you can see that these are then connected via various RF and DC cables to instrument racks. So if we focus now on this this fridge that's circled in red, and now we can take the cans off. This is what it looks like on the inside. So lots of different temperature stages, each going progressively down in temperature, and that bottom plate is sitting at less than 10 millikelvin. And what you have hanging off that are 6 different we'll call universal sample boxes, cylinders, and each of those has its own independent radio frequency and DC wiring that goes up to room temperature and out to a different equipment rack. So a way a user engages with this facility is the user places their device, their sample within one of these sample boxes, either uses existing measurement equipment that's in the racks or provides their own, and the system needs to be opened up. Users attach their sample, the system then gets closed down, and on a typical run, it remains closed, it remains cold for about 2 weeks, in addition to a few days to warm up and a few days to cool down. So in using this system, you're committing to approximately a 3-week run. But the advantage of it is that, of course, because we can have 6 different users measuring in parallel, the cost per day is lower. As I'll say later, we also have a system that has a magnet and a bottom loader where that identical sample box can get withdrawn and reinserted, and that allows users to change potentially on a daily basis, but the cost per day for that system is greater. So yeah, these are one of these sample boxes. You can see with the RF and DC connectors on the top. And this is what it looks like. So you basically have a space of about 78 millimeters in diameter and some kind of structure onto which you can bolt filters, a PCB, various kinds of, whatever you need for your measurements. If it can fit in the box, then to some extent, it can go into the system. Yeah, so as I said, the precise number of lines varies a little bit according to the different bays and the different fridges, but this system allows up to 14 microwave lines, so that's up to 20 gigahertz and up to 96 DC lines. And we have this kind of plug and play access. Our preferred mode of usage, particularly for users, frequent users of the facilities, that they have their own sample box. And that allows the user to get it all ready in advance, and then it's really just a case of plugging it in to the bottom of the system when the fridge is open. And so normally we try to go for only a full sample changeover in 1 or 2 days. One of the biggest impacts of COVID is that we have fewer people in the lab, and so we're now typically taking 5 days to once the fridge is open to change from one set of users to the other. So the system that you've been seeing is our so-called XLD system. It's got this 0.5 meter diameter base plate and these 6 docks for these sample boxes. And as I mentioned, we also have systems that are bottom loaders. They allow the automatic loading of this same sample box, but while the system is cold. These systems have vector magnets. So 611 Tesla means it can do up to 6 Tesla in the vertical direction and up to 1 Tesla in either X or Y. And the prices, just to give you an idea, this XLD system with the different bays is currently costed at £90 a day, but you should bear in mind that there's a sort of minimum booking period of about 20 days, which because the whole fridge is cooled down and warmed up together on this regular cycle. So if your measurement is done after only 2 days, you're still taking up a bay. But these LD 400 systems with magnets have they can be booked in principle 1 day at a time because they have a faster turnaround. But we also ask for a 5K deposit for one of these sample boxes. So not all the fridges have all of the wiring from day one because that would have been extremely expensive. And so instead what we do is we upgrade wiring as and when it's needed. So something we encourage from different facilities. We don't have a kind of automatic online booking system because of the complexity of the tools and arranging access. But if you're interested at the moment, the sort of first point of contact is the email address below. And I'm happy to answer any questions on that. Finally, there's another system which is intended eventually to come into the Quest facility, which is based on a scanning probe system using quantum sensors. And so this is fundamentally based on this AFM confocal microscope with closed loop positioning that runs at very low temperatures. And the idea is to use single defect spins, for example, in diamond, and use them as nanoscale for nanoscale magnetometry at cryogenic temperatures. This is not by any means an off-the-shelf system. It's something that requires quite a lot of development, which is ongoing. But our hope is that eventually that's a facility that could be used for anyone interested in making sensitive nanoscale magnetic field maps. That's it. So.
Great, thank you very much, John. Let's hand over now to Pavlo Zubko, who's going to talk about Xray diffraction. Share your screen, Pavlo.
Yep, I'm just trying to do that. Can you see it?
We can see it, perfect.
Great, thanks. Hi everyone. I'm Pavlo Zubko, and I'll try to be quite brief because I'm only going to talk about one single piece of equipment, which is this Rigaku Smart Lab Xray diffractometer that my group and I look after at the moment. So this piece of equipment is basically located in the physics building right next door to the LCN, and it's essentially a multi-purpose diffractometer. So one of the special features it has, one of the special features it has is this rotating anode source, which gives you a very high photon flux. It has a 4-circle goniometer with a range of different sample stages, depending on what kind of samples you're looking at, whether they're thin films or powder samples. And it has a range of different optics. So it has a cross-beam optics module that allows you to easily switch between a parallel beam configuration for, say, measuring thin films, or Bragg-Brentano focusing optics for powdered samples. And we have a number of monochromators for different sort of trade-offs between intensity and resolution. On the detector side, there's a couple of detectors. There's a 0-dimensional detector, scintillation counter, and there's also a high-speed 1-dimensional silicon strip detector, which is very good for doing quick reciprocal space mapping. Recently, we've also installed a couple of temperature stages on this system. So there is an Anton Par furnace, which allows you to go up to 1100 degrees centigrade. And there's also an Anton Par cooling stage, which allows you to go down in principle to about 100 Kelvin. So this cooling stage is something that we installed quite recently, and because of the pandemic, we haven't tested it fully, but in principle, it's ready to go and should be available hopefully soon. So this is just the cooling stage. The system is actually very highly automated. So it's quite easy to use. It does all of the optics alignment automatically, and even the sample alignment automatically if you want to do it that way. There is a range of different packages for different kind of measurements that you might want to do, and the system effectively guides you through what optics you need to put in and what detector you need to put in, and so on. And there are chips on every bit of equipment that you can unplug, and the machine automatically detects whether you've put the right bit of equipment in. It comes with a range of software. So there is obviously this diffractometer control software, which comes also with a nice reciprocal space mapping simulation tool. And then there is a couple of software packages for analysis, both for standard scans and for reciprocal space maps. So just in terms of the kind of measurements you can do, again, as I said, there are different packages in the machine for doing different kinds of measurements. So you can do the standard out-of-plane measurements. So here all of the examples are for thin films, but of course you can also do it on powders and samples in capillaries. So you can do these theta-to-theta scans for determining the lattice parameters and the film thicknesses if you have films of very well-defined thickness. You can do rocking curves for crystallinity and mosaicity of your samples, pole figures for epitaxial materials to determine textures and orientation of your samples. reflectivity for film thickness and roughness, and reciprocal space mapping. So with this one-dimensional detector, you can do very fast reciprocal space mapping to check for strain relaxation, how coherently your films are grown. And if you have samples which are sort of more complex, for example, the two images, reciprocal space images shown here, are for super lattices and for films with some complex domain structures, then of course you get a lot of information from reciprocal space maps. There's also a small angle X-ray scattering attachments for doing SAX measurements as well. So that's it. The machine is currently being charged at 120 pounds per day or 60 pounds for 4 hours. And so if you're interested in using it, just drop me an email and we can talk about the training and the access to this. I think that's all from me. I'll be happy to answer questions.
Great, thank you, Pavlo. I think in the interests of time, we'll save the questions to the end and plough straight on to Dominic Papineau to talk about micro Raman. Dominic, over to you.
Okay, hello, can you hear me?
Yeah, we can hear you. We can see your screen also. Go ahead.
And you can see my screen. Okay, very well. So I don't know if you can see my cursor, but hello, everyone. Like Pavlo, I will be talking about just one instrument, which is a micro Raman system from the company VTech, which is located in the Geological Spectroscopy Laboratory in the Kathleen Lonsdale building in the Department of Earth Sciences. So this instrument is used primarily to describe samples in the microscopic scales, but in a macroscopic context. And it has the ability, of course, to do these analyses in a non-destructive way. The goal that we most typically use it for is to identify minerals in complex assemblages of minerals in rocks, and particularly those that are associated with organic matter. And this can be quite challenging because those minerals tend to be very, very small, sometimes on the order of just a few microns. So we need high spatial resolution to do that. The technique also allows for the determination of what crystalline phases are present and allows for confocal observations below the surface of transparent phases, which means that we can go a few microns below the thin section surface or a thin transparent crystalline substance and obtain the Raman signal from a confocal plane below. And lastly, the instrument can be programmed to collect a spectrum at every pixel, and therefore we can create Raman images, and that helps to determine the degree of ordering and molecular groups of organic phases and other also inorganic substances. So these are some images of the Geological Spectroscopy Laboratory. We have a nice polarizing microscope with a side scope, which is very useful for teaching. And in the upper right image here, you can see the kind of the enclosure for the micro Raman with the computer displays here, display monitor, and we have a sample preparation area that includes both a small lab bench, a sink, and a fume hood for chemical experiments in aqueous solutions, and then we can look at those as well in the micro Raman. So this is the micro Raman itself. So we have a laser which has a wavelength of 532 nanometers. So it's a green laser, and the spectrometer is located behind the right-hand monitor here. And the overall microscope is essentially an inverted optical microscope. So the images are inverted by 180 degrees, but that kind of optical configuration allows us to reach some good level of confocality, which can be selected by changing the optic fiber diameter here as the pinhole in the topmost part of the microscope. So that pinhole is set by the diameter of the optic fiber, and the smaller the optic fiber diameter is, the thinner the confocal plane that we are looking at is, but also, of course, the smaller the signal that's being collected becomes. And then there's also a photometer with which we can set the power of the laser, which can be set between anything between about 0.1 milliwatts even a few microwatts, but then you don't get a really good Raman signal, and all the way up to, well, it's rated at 65 milliwatts, but we typically don't go beyond 45 milliwatts. This is a class 3B laser, so there is some operational safety guidelines to consider for using it, but we also have a very versatile control software as well as the project software to process data and to do modeling, Lorentz peak fit or Gaussian peak fitting modeling, so that we can determine the areas under the curve. And we have, of course, Papa Smurf to help for good karma. So here are the technical details. I mentioned already a few, such as the laser wavelength and power. The optics, so we have a number of objectives. We have 5 objectives, 5x, 10x, 20x, 50x, and 100x. So we can do, so we typically collect the spectra and the hyperspectral scans with the 20x, 50x, or 100x objective, which gives a combined magnification between 200 and 1000x magnification. At 1000x magnification, of course, we're diffraction limited, so the maximum spatial resolution that we can get to is 360 nanometers. Then we have 2 gratings in the spectrometer detector that we can select. One is 600 grooves per millimeter, which gives a spectral resolution of 4 reciprocal centimeters, and 1800 lines per millimeter, which gives a spectral resolution of 0.5 reciprocal centimeter. We have a good spectral accuracy, which is regularly calibrated with an in-house high-grade, gem-grade VVS-type diamond, and that's better than 1 reciprocal centimeter. And I mentioned something about the confocality. We have 3 optic fibers that we can select from: 25 micron diameter, 50 micron diameter, or 100 micron diameter. And the large area scan.
Could I ask you to round up quickly, please, so we've got time for questions if possible?
Yes, no worries. So yeah, so we can do large area scan up to 2 by 2 centimeters in size. There's a true surface add-on with which we can use a which we can analyze a smooth regular surface in 3 dimension, and we can process data to create hyperspectral images. So I'm not going to go over this in more detail than we typically look at inelastically scattered photons, so those that have lost a bit of energy, and these are those kinds of peaks that we see, which you can see in a number of examples here. For apatite, there's many peaks because it's a calcium phosphate with some halogen elements in there. We can nicely detect the hydroxyl group when we go to higher wave numbers. For hematite as well, we can detect ferrous iron in ferric phases, which can be very useful for maybe some of your experiments. We can distinguish between different types of carbonates like calcite and dolomite by looking at the peak position. And we can look at organic matter in quartz. The bottom right is better shown here in this other figure, which is showing the D band, the disorder band of carbon, the sp3 hybridized carbon, versus the sp2 hybridized carbon of graphite, and that changes with increasing levels of maturity and crystallinity, and therefore can be used as a thermometer, a geothermometer in our case, but a thermometer in general. So these are just a few examples, just to finish, of the kinds of Raman images that we can generate. We can get to quite high spatial resolution, as I said, about 1/3 of a micron, and we can color code those peaks that are indicative of specific inorganic or organic phases in different colors, and then we can create these wonderful images that correspond to the optical images, either in reflected light or in transmitted light. Here are some examples of what we do in our lab with the analysis of microfossiliferous rocks. In the middle here, probably the clearest ones from India, very beautiful ones. And in the right-hand side are some microfossils from the Grand Canyon of the United States, about 1.6 billion years old. And on the left-hand side is a little grain of apatite in turquoise with a coating of graphite color-coded in red. So we can create a beautiful images. And yeah, this is open to to anyone who wants to use it for reasonable use. You just can contact me. I had my email there on the first slide, and it's also on the website. So.
Good, thank you very much, Dominic, and thank you also to the previous speakers, Pablo, John, Steve and Richard. I don't want to run beyond 5:02, so we have time before the LCN general meeting for LCN at UCL people. If anyone has some very brief questions they want to ask of any of the speakers, we have maybe 1 or 2 minutes to handle those right now. Okay, so if there are no questions, I guess the summary of the talk is as follows, that in spite of COVID, LCN facilities are still very much open for business. Hopefully we've given you a flavour of the wide variety of facilities we have available to researchers, be they PIs, postdocs, PhD students from any of the 3 institutions, King's, Imperial, UCL. Please do make good use of these facilities. Of course, there will be some additional restrictions and risk assessment procedures to follow because of COVID, but certainly my experience in my own research group is that in spite of those issues, that it is possible to make good progress using facilities and to continue the research, which is the aim of everyone on this call, I guess. So I guess you have all the email addresses for the various people who have given presentations today. Do reach out to them if you'd like to learn more about any particular piece of kit. There's a wealth of information on the various technical facilities on the LCN website also. But if there are no questions, I guess I'll wind up there and remind people that in 10 minutes time we have the LCN general meeting for people from UCL. So thank you for your attention in this meeting, and do reach out to the people who have been speaking to learn more.